Hello. Good afternoon. Welcome, and thanks for being here. I see people are still walking in, so we have a lot of space on the right side if people need more space. So thanks for coming in today. Before we get started, maybe you can do a quick show of hands. How many of you run big data applications on-premise today? Wow, a lot of you. And how many of you are considering migrating to Amazon EMR? Oh, great. A lot of you. A lot of customers like you have requested us to give opportunities to hear stories of other customers who've recently migrated to Amazon EMR. So this is Al, a product manager with the Amazon EMR team. And I have the great privilege of welcoming two of our premier customers, Lending Club and Thomson Reuters, onto the stage today. Now, these two customers come from very diverse backgrounds. They have very different workloads and use cases. But what's common between the two of them is that both of them migrated from a on-premise big data application stack infrastructure to Amazon EMR to build their big data platform. And they were able to both reduce costs and simplify their operations while doing that. To kick things off, please join me in welcoming Sam from Lending Club to the stage. Sam?
Hi, everybody. I'm Sam Scrow. I'm Chief Architect and Head of Consumer Engineering for Lending Club. And I'm really happy to be here on behalf of our data engineering team to talk about our successful migration from an on-premise data center into Amazon, all with the help of EMR. We'll talk a little bit about our workloads, the challenges we faced, and how we eventually overcame them. And I'll leave you with a couple of tips on cost optimization at scale. So let's talk a little bit about Lending Club itself, right? We're a direct-to-consumer digital bank. We specialize in providing consumers easy access to low-cost credit, all while still giving great returns to our marketplace of investors. We're one of the original fintechs. We were founded in 2007, and last year we became a bank. So now we offer a balanced set of lending, spending, and savings products to our 4 million members. Affordable lending, though, is still at the heart of what we do. We originate over $3 billion of loans per quarter. That's $80 billion since the launch of the company, which is, frankly, just wow. To be successful at that scale, it's our credit decision models, the associated decision science. They have to make millions of successful and correct predictions each year. It's through effective access to data that we make this happen. We compile over 2,000 attributes that help us understand our customers. What do they do when they get to our website? Which offers do they look at and decline, and which ones do they take? And ultimately, some extracts from the 75 million historical loan repayment events that have happened through our platform since 2007. All in all, that's 10 terabytes of new data we have to ingest every day and 1 petabyte in active use. Internally, all of this powers the analytics and reporting for over 1,500 internal consumers across 15 teams. They use it to make a variety of their day-to-day decisions happen, predicting what marketing is going to appeal to a specific segment of our customers, trying to figure out who might be on the verge of going delinquent so we can do some proactive outreach and pull them back. And lastly, it's the constant training and retraining of our models. For years, we accomplished this in an on-prem data environment running a commercial Hadoop distribution. Data is sourced from our internal databases, log files, and some third-party data sources, all with permission from our customers. The workload is largely batch-based Oozie workflows that drive Hive SQL. We have about 550 critical pipelines that are the backbone of what we do. In execution, it's supported by a cluster of about 100 servers, 19 terabytes of RAM, 1 petabyte of storage, mostly on local disk. Clients are accessing files on it via HDFS. The files are in ORC format. And we maintain an identical replica in a backup data center for high availability. The actual layout's really, really simple on-prem for us, or it was, just one single multi-tenant Hive cluster. And beyond just the regular reporting and analytics that we would drive, that we wrote ourselves, we would allow for ad hoc reporting by our customers using Presto, Tableau, SAS jobs, or just driving plain old JDBC connections. Now, Lending Club does do a fair bit of its day-to-day application workload using eventing. We stream a lot of data into Kinesis, but I'm going to save that for another reInvent talk. So let's break down our workloads a bit, and hopefully this is something that might resonate with you and your businesses. The first core that we have to drive is plain old ingest and transform classic ELT. These are batch jobs. They kick off at a set time past end of day, and they're very urgent. They have tight SLAs, and they gate everything else downstream. They're also very predictable. We know when the flood of jobs is going to kick off. We don't get a lot of surprises. But if we miss a job by an hour, Rahul here in the front row gets an angry call from somebody in the business. And if we miss it by a day, we've definitely ruined his week. Now, with analytics, we've got a mix. We do have these critical, urgent jobs that we have to make sure get done by a set date. We've got to make sure our investors know how their portfolio of loans are performing. We've got to help the risk team immediately understand the loan repayments that are happening for our newest cohort of borrowers. But ultimately, we also enable a lot of ad hoc requests. There can be a lot of surprise surges happening there. We have to hold back a little bit of burst to make sure they can get done. And lastly, we have our decision modeling data science workloads. These demands, they tend to surge and ebb with the macroeconomic environment. If it shifts, we've got to shift. And ultimately, if we're shifting, we're tweaking our models, we've got to back test it. How are these models, how would they have performed against all of the loans we've ever issued? Now, again, these are not very predictable. You can't predict the market. We never know when these are going to hit, but we can schedule around them a little bit. They're also very, very burst hungry. They'll happily soak up all the resources you throw at them. That's going to improve accuracy and the predictions they're making. So how did our on-prem environment do for this? So this is a graph. It's showing the amount of memory used in our cluster mapped across a typical 5-day work week. What's the first thing that jumps out here for you? Well, for me, it's those flat caps. Okay? What they represent is stress. We've taken everything we've got in a cluster. We are throwing it at these jobs. We've held nothing back. There's no more burst remaining, no more elasticity. Unsurprisingly, this corresponds to those time-sensitive jobs, right? If something fails, we're in trouble. Now, we also got these deep, deep valleys. We're not doing a lot of this with this hardware when it's idle. That's wasting money, power, cooling, attention from people. Now, I mentioned that we've got burst workloads, and they could soak up all those resources. But again, we've got a single multi-tenant Hive cluster. If those jobs run a bit late, they run a little bit over, they're eating into the SLAs, and again, Rahul's getting a phone call, right? So we're in a very stressful situation. It really meant that upgrades were next to impossible for us. Sure, we could have used our backup environment for burst jobs or potentially to test upgrades. But again, it's supposed to be sitting there as a failover. We can't muck with it too much. And ultimately, what that meant is we're going to test those upgrades in non-production, non-representative workloads. So we get to production and find surprise failures. We start missing SLAs. Jobs start missing data vanish, surprisingly, right? It meant that upgrades, it created a culture of fear. We weren't going to lean into an upgrade and get access to new capabilities, like column-based partitioning, or frankly, anything that might let us get away from our multi-tenant environment. So ultimately, look, this is impacting business agility. It's impacting predictability. We have to do better. So the obvious goal, the obvious destination is the cloud. We're not going to have any further problems bursting to hit that capacity. And we were also very comfortable working with Amazon. Our application environment was largely in Amazon at the time that we were making this decision. We could get greater resiliency. We could have nodes that basically, instead of having to, again, deal with them as individual pets, we can treat them like cattle, right? Kill and fill. The dead nodes are going to auto-recover. We can roll out upgrades cluster by cluster, or even rolling within a cluster itself. And really, we felt that if we could just tune the workloads to the hardware we had, we could lower the overall cost to actually run them. And lastly, we'd been walled off from new upgrades for ages. In Amazon, you get everything that you need. You get a variety of integrated services, S3 to SageMaker. Partners are there already. You snap your fingers, and you've got a lab environment ready for you to experiment. Amazon has everything that we need. But we're still stuck with one key question. What are we going to do for our actual Hadoop software itself? What distro are we going to use? So we had a couple of obvious choices. The first was to roll our own, right? We're comfortable using open source, no problems there. But if you think about it, we're going to have to collect the packages, harden them, test them. We're going to have to do all that work, and we're not necessarily a massive company. It seemed like a waste of resources. Our second choice, look at a commercial vendor. And we did this and ran down this track for quite a while. After all, even our commercial on-prem vendor had a solution for Amazon. They're going to give us commercial support. They're going to give us hardened packages and some closed source pixie dust, where they claim that they're going to beat Amazon at its own game and do better. Well, frankly speaking, what we found out after a little while was that basically we were not getting those promises. We were getting inconsistent support. We were not finding the promises. We were getting broken promises. And ultimately, the price to performance, it just wasn't there. And our last option was looking outside of Amazon itself. Some of the other larger cloud platforms have a great big data story. But ultimately, we weren't really ready for multi-cloud. We were on Amazon already. It didn't really seem like it was, the juice wasn't really worth the squeeze. So ultimately, that led us to EMR. With EMR, we get all the tools that we need to run our current Hive workloads, as well as everything we need for the future. Iceberg, Hudi, Spark Streaming, being able to adopt to streaming jobs with Managed Kafka. Plus, it's not just EC2. We can be running these containers on Kubernetes. We can be running them serverless. Secondly, we're a big Terraform shop. We use it to manage most of our cloud resources. EMR works perfectly for this. So managing multiple clusters, dealing with auto-scaling and tuning, no issue whatsoever. We'll be able to handle that elegantly. And lastly, we're a tech company. For us, using open source is kind of in our DNA. It's our active preference about what we'd like to do. And even through this migration, when we ran into issues, we were able to go under the hood for the software packages, find the issue, and work with the EMR team to get it patched. It actually worked really well for us, and EMR really got us there. So ultimately, how did we choose to go over? Our choice was to do a lift and shift. So that is the same workloads, the same sources, but in this case, we're going to use some Amazon features to get those advantages I spoke about. First, we're going to do our batch pipelines into a dedicated set of data engineering clusters. Multiple clusters per workload, in fact. No more job contention, and frankly, isolated environments. We're not doing HDFS anymore, we're doing S3. We took that opportunity to catalog our content, splitting it up between raw, cleaned, business level aggregates. We were able to do the same for our analytics workloads. No more contention with the burst the ad hoc workloads need versus the regular analytics jobs. And lastly, decisioning. We can finally run all those cool, quirky retraining, new model investigations those teams wanted us to do. We can fire off millions of requests against our decision engines, which are conveniently also running on containers on ECS to get this done. So really, pretty good plan for us. Now, underneath it all, we also get access to great governance, options for metadata management, role-based access control. It's a pretty good plan. We're going to get a lot out of it. So if you're going to do a lift and shift, what you're really signing up for, though, is a like for like. It means that whatever runs in the data center, the 550 pipelines generating 3,000 tables, it's got to run the same way in Amazon. Identical inputs have to create identical outputs. That's what your goal is. So we had to create some tooling. One of the first things we wrote is a simple data validation framework. After a day's run, what we end up doing is counting row by row and doing row by row checksums, in fact, to make sure what's in the on-prem environment in Amazon are identical. So let's say you find an issue. It could be the jobs, but it also just could be the source data. So we wrote a data validation, a data replication monitor. In this case, it would tell us how replication is doing, and with the click of a button, we would be able to replicate a table, a database, whatever we need to recover. Now, great, we've got the data, it's accurate. It's not going to help us, or certainly not going to help Rahul, if again, we're 6 hours late. So at this point, we need to meet or beat those SLAs. So we wrote an Uzi monitor in this case. It tells us, hey, did the job complete successfully? And if so, how did it compare to the on-prem timing? Great, we've got tooling, we've got a clear target. Should be just a walk in the park, right? Well, unfortunately not. So let's talk a little bit about some of the things we ran into. And one of the most significant shifts that hopefully is clear to any of the veterans in the room is we were going from HDFS to S3. And they do not work the same way. Take any successfully running job in any data environment. Whether conscious or not, you've baked in assumptions into how that job functions and operates. They're baked into the job itself. You change the data fabric, suddenly a job goes from completing in 10 minutes to 10 hours, and you've got to deal with it. So let's talk about how HDFS works. Clients talk to a coordinator, a name node that tells them where content is. It handles block operations. But the bulk of the traffic is happening between client nodes and data nodes for reads and writes. And there are no intermediates. It's a direct communication. And in our setup as well, we're running the data nodes on the client nodes. So effectively, you might be actually fetching content from localhost, which is pretty quick. S3 works very differently, right? There's nothing resident locally. In this case, you're going to a central VPC endpoint for all your requests, metadata or not. And it, in the background, through the magic of S3, mapped the logical path. It's going to get the corresponding physical resource and return it to you. Fundamentally, these architecture, they work differently. They have different performance characteristics. HDFS generally has fewer intermediates. It's going to start getting a response back to its request faster than S3. It's going to handle higher IOPS, higher volumes, lots of little requests. Now, S3, on the other hand, has some advantages too. You can almost think about it being wider. It can tolerate the entire cluster starting to fetch an individual file, with tuning, granted. And it's not going to bottleneck like it might on one of those individual data nodes. Now, that's pretty much where the advantages, I would say, I'm a little biased, end for HDFS. You want to achieve the elasticity. You want to achieve the uptime or durability of S3. Good luck, you're throwing a lot of money at this problem. And ultimately, S3 has a lot of cool features too, right? Cost management with Glacier, versioning. There's a reason why it's the universal data fabric on Amazon, right? Now come back to our problem, right? When we were converting jobs, when we were running them on Amazon, our SLAs were all over the place. And why? Because we had HDFS jobs that were working with directories with millions of files. They were firing off lots of little requests to a highly indexed file format like ORC, instead of brute forcing, potentially, an S3 file request. That meant we had to do a lot of refactoring to get jobs to work acceptably in both environments. Incidentally, this is where the vendor I mentioned earlier came into play that I will not name, promised us they could make S3 work like HDFS. Don't believe the hype. It absolutely did not work that way for us. So to make S3 work for us as well, we had a couple of other challenges we had to overcome. What we found is that as we were hitting peak load, S3 would start complaining, start pushing back on us, giving us 503 slowdown errors. What that represents is that we're hammering behind the scenes a physical resource too hard. To protect itself, S3 is getting us to back off. So what we were able to do is to work with the S3 team themselves. We built a simple log miner. It figured out which paths were actually hitting those 503 slowdown errors. And the S3 team was able to reshard content and actually maybe even allocate some additional physical resource to remove that. And that's a really significant advantage. Otherwise, we would have had to restructure our core file formats going over. The other piece, I mentioned before that we've got lots of little files. We had to refactor jobs to no longer omit them. But as well, we had to deal with the historical directories as well. So we wrote an ORC compactor. It crawled those directories and compressed all the little files into individual larger partitions in order for us to be not surprised when suddenly a job that needs data from a year ago starts misbehaving substantially. We also had some other things. They might have been individual to our migration journey, so keep that in mind. The first thing that we kept running into was data replication or copy timing issues at peak load. So maybe it's the second Thursday, maybe it's the end of the month. Regardless, under load, we'd suddenly start finding blips throwing off what we expected to see. And that was because we had some naive assumptions about when copies of data were being taken and how they were being taken. So we had to deal with that. We had to effectively back those out, fix those issues. So don't take that for granted. The second thing is we had to unwind all the upgrade pain. Remember, it'd been ages since we'd done a big upgrade. We were going from Hadoop 1 to Hadoop 2, from Hive 1 to Hive 2. And what that meant is we had to fix a lot of weird things we hadn't expected. Hive 2 no longer tolerates doing implicit casting when you're doing a join between two tables and there's two different data types. We were using keywords in our queries, in our structures, in our tables that were now reserved in Hive 2. All of that had to be refactored. And lastly, if you've ever done any major JDK upgrade, you always know there's some weird things in there. I've definitely got the battle scars from hunting down time zone issues myself. Lastly, we basically ended up giving up on running Hive to meet the SLAs for some jobs. We pulled them over to run under Spark instead. And that had its own quirks. For instance, the Hive orc reader, it actually skips over Hive subdirectories. We ended up with data loss for some of our jobs. We ended up falling back to the Hive CERD instead. And so again, your mileage may vary, but we did run into a variety of weird issues. The team's here and happy to trade war stories with you if you've got any questions. Lastly, we had to achieve better scaling. So in this case, we're very happy to report that EMR managed scaling, it's really awesome in practice. It's leaning into an array of additional yarn metrics, taking snapshots more frequently. It's much more prompt to scale up or scale down when cluster behavior is changing. We did run into one issue, though, that you might see around shuffle data. So just as a bit of background, shuffle data is when a downstream task, it's going to need content from a task that happened earlier. Imagine for a join or an aggregation. So in our simple example here under Hive, the TES application master, it's telling the reducer to go get content from an upstream map node. It's going to go fetch it and continue on its way. Works perfectly. Well, we were running into issues when we were scaling down nodes, or EMR managed scaling was scaling down nodes. In this case, what we would find is it would shut down an entire node when an upstream task completed. What that meant is the downstream reducer wasn't aware of that. TES wasn't aware of that. It would continue trying to fetch that content. It would fail. The task would fail. That would lead for the job to fail. Ultimately, really what it was, Hive, EMR managed scaling for Hive, it's just not shuffle aware. Instead, what we fell back to is EMR auto-scaling, doing scheduled scaling up and down during peak hours. We are happy to report, though, as of 5.3.7 and 6.7, the Spark integration for EMR managed scaling, it works perfectly. In this example here, although the container is completed and shut down, the node's going to be kept alive until the downstream executors have fetched the shuffle data it needs. Now, we ran into an issue, back to the open source theme, right? It wasn't working for our SSL connections, our SSL-based clusters. We worked with the EMR team on a patch, and as of, again, 5.3.7 and 6.7, the feature works flawlessly. Let me leave you with a couple of other tips about scaling EMR in practice. First, think ahead to your network configuration. Sure, your plan might require you to run 400 nodes at peak, but if you're trying to fit that into a /24, good luck. VPC reconfiguration on the fly is absolute agony. Definitely think ahead to what you're going to do there. Second, we were trying to do too much in our bootstrap phases. We were pulling down internal resources, external resources. It meant that when EMR managed scaling, auto-scaling, or giving the instruction to start up a new node, it took longer than you'd expect. It was unpredictable. So what you want to do is what we did. We baked that software, everything that wasn't strictly needed in a bootstrap phase, into the AMI itself. That will definitely improve predictability for scale-up events. Don't also forget scheduled scaling. After all, we just gave that example for Hive. That's how we're managed scaling as well. It's very useful if you're trying to puzzle out a workload and you're not sure what metric will drive it yet. And on that note, don't be scared of using custom metrics. For Presto, the ad hoc query executor, what we were running into is the typical array of metrics weren't working to predict when to scale up Presto and scale it back down. So instead, what we constructed was a custom metric, a combination of the number of queries running on the cluster and the number of queries waiting. It works very well, and I believe we're rolling out to production shortly. So where are we today? We made it. We're 100% in Amazon. We're decommissioning servers as we speak. There should be a very exhausted set of party horns on this slide that are missing. So look at that graph on the bottom. It's basically what we were showing you before, but now that peak is nice and jagged, right? We're not having these artificial caps. Every color you see there is an individual cluster, all running workloads. And we're bursting above 100 terabytes of RAM, far beyond the 19 terabytes we can marshal in the data center. And why is that too? Why are we going so much above? Because we're able to run those new and complex decisioning workloads we couldn't run before. Now we can absolutely run them on Amazon. And generally, for those workloads that we're running on the data center, we're on track to realize a 15% savings in the total cost of operations, which we'll talk about in a few slides. Our business, pretty pleased with us. That's a 99% SLA compliance we're reaching. On the left, you can see the timings of our high priority, medium priority, low priority jobs, P1, P2, P3. We're either hitting the timeline or beating it by 2 to 3 hours now. This is unheard of on-prem for us. And our security team is also a bit happier as well. We've gone from upgrades on a timeline measured in months to 4 upgrades over the last 3 months alone. Now, all that burst does not come for free. Okay? When we started off in May, we were running default configurations, just what basically came out of the box, as long as we met our SLAs and the data was correct. Just through focusing, and some of the steps we'll talk about in a minute, we managed to reduce our overall spend by 22%. And the way we did this was focusing on a particular methodology, which we're going to share today. But again, it's never too early to start planning cost optimization. It's a never-ending process in some ways. You always have to be engaging with it. Use Amazon's tools. Don't be scared to set up budgetary alerts. You have to focus on this. So the first thing we did was focus on the jobs. It's probably pretty obvious. There's no point paying Amazon for a job that, while meeting its SLAs, is really not performing to the peak of its ability. So at this point, we built some simple Splunk queries. They would take Yarn applications and extract out a measure of the CPU and memory time that they were taking to run. We produced a simple cost metric, and with that cost metric, we were able to add those all up using Oozie workflow tagging into the overall cost of the workflow. That gave us a clear indication of where we should focus our efforts. Not a guarantee that the job is misperforming, but definitely the greatest bang for your buck is going to be coming there. The second, now we had to return our attention to the clusters themselves. I've come back to this a few times. I'll repeat it again. You definitely need observability. This is a Grafana dashboard that we're pulling from our environment. We run Prometheus as our APM. So on the top, what you're seeing is memory usage across the cluster at the OS level. And then below, via CloudWatch, it's Yarn metrics, what's being emitted by the cluster itself. In fact, we went further. We actually created our own custom metrics generator on Spark executors so we could get more detailed statistics. With that in hand, it's time to start properly sizing the containers themselves. In this case, we really wanted to make sure the container was using all the resources dedicated to it. And we often found cases where we were overtuned. To that end, we tracked Hive and Tez task counter metrics, and again, that custom extract of Spark executor metrics, and we used those to tweak the Yarn config. Then with the containers running well, how tightly can we pack them into the instances? Again, we were finding out that we were over-provisioned. We could lower down instance sizes, and in some cases, we can shift instance families to get more of the resource that's bottlenecking the job itself. And then finally, we can turn our attention to optimizing how much we're paying Amazon. And anybody who's been doing this for a while knows the number one enemy is on demand. So in this case, we have, since the start of the project, we've been able to do about 19% reduction in how much on demand we're actually using, which is great. We're using savings plans. We prefer them to reserved instances. Gives you a lot more flexibility to shuffle across instance families and the like. But you'll also note there how little Spot is as a percentage of the overall spend. And that's something the team is working on right now. We're going to share a few insights that we've had in practice. So when you have a long-running cluster and you go to Spot and say, hey, Spot Instance Advisor, tell me what instances I should be using to get the cheapest price, it's going to make a recommendation. But things change. What's true on Monday is not true on Friday. Maybe you're drowning in M5s, but then by Friday it's all C-class instead. So that's what we would encounter. Over time, our long-running clusters would start experiencing more interruptions, more Spot launches. And it seems obvious when we explain what the phenomenon actually is. So what we're actually doing is a wholesale rethinking of how we're running some of these clusters, shifting more of them to ephemeral workloads where, again, the Spot instance prediction will match up and line up perfectly with the actual workload. OK, so I'm just going to leave you with our future plans. The first thing is getting that Spot rolled out in production and non-production. We think there's a lot more bang for a buck, and we can continue driving that number down. The second thing is we've been very comfortable using EC2, but we're also very comfortable using containers in some of our other environments. Trying to investigate that, potentially looking at serverless for some of our ephemeral workloads. Now, Orc's been great, but the world has moved on. So we have a lot of workloads that would be much more comfortable, much more efficient if we were able to do inserts, updates, ACID-compliant transactions. At this point, we're investigating Iceberg and Hootie because those are supported by the EMR team, as well as some commercial options. And lastly, I mentioned streaming and passing. We do see a lot of opportunities where instead of that big burst, that big batch, we might be able to trickle feed content through the day. And we think for certain use cases that will definitely help the business out, make more dynamic decisioning on just how we're performing in production. All right. Thank you all for listening. I really appreciate your time. I'm going to hand this off to John Engelhardt from Thomson Reuters. Good stuff.
All right. Thank you, Sam. Great presentation. And Al, I want to just say thank you for allowing me to present today, and everybody for coming out and listening to me speak. I want to start today's presentation off with a question. And that question is, have you outgrown your on-prem Hadoop systems? Do you have this feeling in the back of your brain that it's only a matter of time until you've outgrown your on-prem Hadoop systems and it's just going to become obsolete? Well, I want to walk through some indicators today to maybe show you that it's time to migrate to the cloud. So the first indicator is Are you starting to have meetings with your business partners where they come up to you and they say, I've got this use case. It's actually more complex than what you usually are requesting. And then you have to make compromises with them because you know that your on-prem systems just can't provide what they want. Are you starting to realize that upgrading your Hadoop cluster is becoming more difficult? Because you started out with a Hadoop cluster 7 years ago, but over the course of the time, you've added more and more workloads, and testing all of those to do an upgrade is a lot of work. Do you have an inefficient build and deploy and workflow orchestration process that makes your time to market frustrating and slow, and all of your developers really just don't like working with it? Are most of the people at your company not actually big data engineers? They're just traditional Java developers. So that them actually interacting with HDFS or trying to get access to your Hadoop cluster is actually challenging. Or anytime you have new business requirements and you have to refresh or purchase more hardware, you have to wait a bunch of time, and you keep getting more hardware, and you have this growing licensing cost that is kind of getting out of hand. Well, we had outgrown our on-prem Hadoop cluster, and today I want to share with you the journey that Thomson Reuters took to migrate to the cloud. So my name is John Engelhardt, and I have been on the ground floor the last 2 years migrating our on-prem Hadoop systems to AWS at Thomson Reuters. Most of you have probably heard of Thomson Reuters as a global news provider, but what you might not know is that Thomson Reuters is the premier legal research platform, Westlaw. Every single day, legal professionals are doing legal research. And you might say that the difference between winning and losing a case in the courtroom is decided by the data provided by our on-prem Hadoop clusters. So as we migrate to the cloud, we cannot impact our customers. No pressure. So today, I want to share with you what our on-prem Hadoop looked like, some of the challenges, and how we were able to migrate without impacting customers. So as I mentioned, big data powers Westlaw, Thomson Reuters' legal platform. But see, most engineers at Thomson Reuters are not big data engineers. They're responsible for single sets of data. They go out to a court's website, they acquire that data, they normalize that data, they enhance that data, and they publish it. It's a very straight line. But the big data environment is the one unique place where we replicate the hard work of all these different groups at Thomson Reuters. And that allows us to bring all of the different content types into one place. And that opens up endless possibilities. It's where we can create cross-content set functionality, allowing us to group and aggregate different things like case law, statutes, regulations, and try to find meaning between all of the data sets. The big data environment also gives us the ability to retro all of our content. You see, legal professionals do care about content currency, but they're not usually looking for the newest court document. They're looking for the perfect court document. They're looking for that 1 in a million court document, and they will spend hundreds or thousands of hours doing legal research on Westlaw to find that document. When they find that document, they can walk up to the judge and say, this court document is identical to my client, and they'll win their case. But see, we need the ability to try to find those documents, present them easier for the customers so they don't have to spend hundreds and thousands of legal hours doing research. So every time we come up with new search capabilities, the big data environment is a place for us to run all of our algorithms across all of our data. Because that 1 in a million document we might have owned for 20 or 30 years, but it was only easily found by something we just recently created. So over the last 5 years, Westlaw has released 2 major versions of their product, Westlaw Edge and Westlaw Precision. And a huge part of those features are running on the data that we pre-compute every single day. So let's look at what the big data environment looks like. As you can see, it's incredibly messy. The purple boxes are data sets. It tells you who wrote them, and it tells you every single person that read from it. And the blue lines are transformations from one data set to the next. It's not a simple straight line. So migrating this data is incredibly difficult because when you have 300 workflows and they're all reliant on different parts of data, it's very challenging. So let's look at how we created this data in this graph with our on-prem systems. So on our left here, we have our traditional data sources. These are what the traditional engineers at Thomson Reuters are responsible for, the data they acquire. On the far right, we have our products. This is what our customers interact with. But in the middle, we have our on-prem Hadoop system. And here, we're replicating that hard work, that data, into Hadoop. We have a bunch of jobs that will create normalized intermediate data sets and put them on HDFS. And then we have additional jobs that are going to create business features, and we're going to push those out to the customers. Let's look at a few problems with this architecture. And the first one is multi-tenant clusters. If you don't know what a multi-tenant cluster is, it's a Hadoop cluster that can have many users or many workflows running on it concurrently. And this works great in theory, but in practice, it has a lot of problems. Because as you add more workflows and you purchase more hardware and you kind of repeat this cycle for years and years, you end up with monolithic multi-tenant Hadoop clusters. And when a single workflow becomes a noisy neighbor, it can kind of impact the whole Hadoop cluster. Or if the Hadoop cluster has stability issues, all of your workflows could be impacted. The next challenge that we wanted to address was our DevOps. We were using Jenkins for our builds and deploys, and we were using CDAP for our workflow orchestration. From a Jenkins perspective, we couldn't deploy into CDAP while the workflow was running. And when you have 300 jobs running at all different hours, there were certain jobs that were running, and the only time you could deploy when you were sleeping. From CDAP's perspective, it was in charge of orchestrating our workflows. And it did a great job until it just sometimes didn't, right? Once a month, maybe the job just wouldn't kick off when it was supposed to. And this makes it frustrating from a developer's perspective, but also really hard to support from an operations. And the last challenge was around hot redundancy or active-active. And it all goes back to multi-tenant clusters. We learned pretty early on that this massive multi-tenant cluster could have huge impacts if it was having problems. So what we created was an identical Hadoop cluster in a different data center. And we put all of our workflows on that one, and we ran them both every single day. And then we created additional code that allowed us to say which cluster is going to promote data to the customer. Because of this, though, it causes all sorts of problems, from trying to keep your data in sync between two clusters, to doubling your Hadoop clusters, to doubling your licensing costs. It was a frustrating experience. So now that we've looked at some challenges with our on-prem systems, let's look at some challenges we faced while migrating to the cloud. And that first challenge is all about migrating workflows incrementally. You see, our business partners told us as part of our migration, every single quarter we had to decommission a percentage of our workflows. That meant it was running in production AWS, and it was no longer running on-prem. And that's a very difficult ask when you look at that previous image and all of our workflows are reliant on other workflows. So let's look at this simple example where we've got a timeline. And the first workflow creates a data set, but it takes 70% of your workflow time. And workflow 2 is dependent on workflow 1. And workflow 3 is dependent on workflow 2. And you might think, well, just do them sequentially. But that just doesn't work because that adds up to more than 100% of your work or your migration timeline, and you're going to fail. And this is just 3. When you have 300, there's no way you can do it. So how were we able to migrate incrementally? What we decided to do was create a bidirectional copying system. and that enabled us to migrate incrementally. The first direction is copying data to S3, and that enables us to run our workflows in AWS. The second direction was copying data back to HDFS, and that enabled us to decommission workflows running on-prem. All of this was achieved through using distributed copy, allowing us to copy terabytes upon terabytes of data to and from AWS every single day. So let's look at that same timeline and apply this. Focusing on workflow 2, we want to start its development right away because we've got developers queued up. In order to do that, we're going to copy its required data set to AWS. And then workflow 2 finishes its development, and we want to get it into production AWS. But we can't do that because workflow 3 is reliant on it. So we're going to copy workflow 2's output back down to on-prem. And this allows you to start untangling the web, and you can cut out workflow 2 while not impacting workflow 1 and 3. The next challenge we had was all around coordination and consistency. You see, we had 50 developers working on this project. We had 3,000 Spark jobs we needed to migrate, 300 workflows. How do you do that and have all of them look and feel the same? I want to be able to open up any GitHub repository and understand exactly how it's working. So it starts with shared frameworks. Shared frameworks are things that every workflow will use and build on. A couple examples are golden AMIs or bootstrap scripts. Centralizing those allows you to make a single change in one spot and apply it to every single person that's using it. In addition, shared utilities are like frameworks, but they're actually pieces of code you're going to import. What we found was wrapping things like the AWS SDK with convenience methods, so our developers who had never worked with AWS before didn't need to learn all of the different technologies. They had very easy ways to interact with it. We also created a utility around cataloging our data, which allowed us to write to the catalog and read to the catalog. So speaking of cataloging data, we didn't have this concept on-prem. How we shared data between workflows was dependent on the year and the developer who wrote the job on-prem. Some developers decided they were going to write a metadata file on HDFS and said, go read that file, it's got a pointer to tell you where the data is going to be. Some people used Hive views and said, we'll manage the underlying data for you. Some people wrote dated files and said, go sort the dated files and then go check the newest date and make sure there's a success file in there. That's how we're going to share it. This was really inconsistent and frustrating, and you had to write a bunch of custom code, and then people would do it wrong, and they're like, why don't I have the newest data? So because we decided to make a utility on how to read and write the catalog, it made it really easy. It was one of the most important parts because it didn't matter if we were copying data to S3 or we were using the actual output created by a workflow running natively because the catalog had the pointer. That workflow just changed it, and the consumer of that didn't even matter. We took it a step farther, though, and we built APIs on top of our catalog. And then we made a UI that we exposed to everybody in our company, which allowed anybody, even if they weren't in our AWS account, to see the metadata of all of our tables. The next thing is creating a small group of experts. Understanding that AWS's landscape is massive is really important, and everybody can't know it all, especially when you're coming from a spot where nobody knew any of it. Have a few EMR experts, a few Spark experts, a few people that specialize in CI/CD and rely heavily on them. So not everybody's reinventing the wheel. And the last one is make sure you're doing proper tagging. And we also created a custom compliance bot to enforce those tags. Cost allocation tags are really important because they allow you to slice and dice your data and your costs of all of your workflows. Having the ability to say which group of developers is costing the most amount of money, which GitHub repository is costing the most amount of money, but most importantly, which individual workflow is costing the most amount of money is incredibly important. Because I can easily now go and check and see what are my top 10 most expensive workflows. And I know that certain ones in there shouldn't be in the top 10. So I can go and I can audit those because a developer that migrated that workflow might have not been an EMR expert. So they wrote a Spark job on an EMR cluster. They had a massive EMR cluster and a small Spark job. It was a mistake. They didn't know, but you need to be able to understand that. The compliance bot we created enforced that the required tags were there. Every 15 minutes, we polled every single running EMR cluster and made sure the tags were on those clusters. If they weren't, we terminated them. We also created an uptime tag, which basically said, how many hours can this cluster be up for? If a cluster had an uptime of 8 hours and was running longer than that, it would get terminated. You see, this was really important early on when we had a lot of developers making ad hoc clusters that should have been up for 2 or 3 hours, and I would find them running for 6 weeks. It's not a bill you want to have to deal with. The last challenge that I want to share with you guys was all around content currency. You see, our business partners would always come to me and say, hey, John, I really like what you're doing. I wish you could do it faster. And there was 3 major reasons we couldn't do it faster on-prem. The first one's notification-based workflows. We didn't really have this concept on-prem. Most of our workflows were running based off of time. Workflow 1 ran for an hour. Workflow 2, what we wanted to run after that, we would kind of stagger it by an hour and 15 minutes, and we would pray that the first workflow didn't run longer than it needed to. Taking that notification-based workflow into the next point, we had some workflows where the first one finished, and we wanted to kick off another 50 of them. But on-prem, we have a static set of resources. It's a rectangle. So when we would kick off those next workflows, we would have to stagger them, run the first 10, then the next 10, then the next 10, so we could run all of our workflows. But in AWS, they give you the ability to run all 50 the second that first one's done. And you can have high peaks and low valleys, and you're not paying for the static set of resources, playing the game of Tetris, where you're trying to finesse how all of your workflows are going to run. The last one is we redesigned our most important content. You see, our most important content was getting to our Hadoop cluster in approximately 12 hours every day. We were able to get that down to approximately 5 minutes by leveraging Apache Hoodie. If you don't know what Apache Hoodie is, I recommend you go read about it, but it's effectively Parquet with the ability to do incrementals. On the left, we have our enterprise content storage system, and we created a replication system for that, where every single transaction that occurred was put on a Kinesis message, saying it's a promote, or it's a demote, or it's a bulk of all of the data for each content type. That transaction message written to Kinesis had a pointer to all of the data that changed on S3. So all of the records in that transaction were also then written to S3. With those 2 components in place, we were able to create a Spark streaming job running on EMR that ran every 5 minutes, and it grabbed all of the transactions that occurred in Kinesis during that window. And then it would go read its corresponding data on S3 and get a data frame. Apache Hoodie then gives you the ability to do what's called an upsert, which allows us to write our bronze data right there in the middle. Apache Hoodie has a merge on read table, which gives you the ability to do random, high-volume updates without blocking. And that allowed us to keep that middle data set up to date with our enterprise data storage in 5 minutes, which is usually 12 hours. But then we took it even farther. Hoodie gives you the ability to know the differences between commits because they keep track of what's called a commit time. So from there, you can, instead of having to just recompute the world every day, you can say, give me the difference from the last time I successfully read from you. And that allowed us to just get the deltas between when we ran. So we could create more streaming jobs reading from Hoodie, or we could create hourly or nightly batch jobs. And that allowed us to create our silver and our gold data sets, which then all of our business features would do their aggregates off. So now that we've looked at some challenges, let's look at what our architecture really kind of fleshed out to be. On our left, we still have those same traditional data sets, and on our right, we still have our customer-facing applications. But in the middle, we have our big data migration all running in AWS. There's no more on-prem Hadoop. And it all revolves around EMR. So let's look at a few key benefits that we did. The first one is we decided to store data on S3. Storing data on S3 means that every single EMR cluster can interact with the same data set. Not only can our workflows interact with that data set, anybody at Thomson Reuters can request access to that data and we can share it. It allows us to catalog our data significantly easier as well. It also means that our EMR clusters don't need to be persistent. We simplified our DevOps process as well. We went to code pipeline, code build, and cloud formation that gave us a true environment and stack where we could roll our code up the environments. We knew that we had some testing shortcomings on-prem, so as part of every single CI/CD pipeline, we baked in a step function that would execute the entire workflow with a set of gold test data, and we would validate the output so that we weren't deploying code that wasn't tested, something that was happening before. The last one and the most important one is ephemeral clusters. If you don't know what ephemeral clusters are, they're short-lived clusters. They only run as long as you need them. And we took this concept to the far extreme, and we decided every single workflow would be its own EMR cluster. No longer do you have a multi-tenant cluster. No longer do you have noisy neighbors. If your workflow fails, it's because your code isn't stable or your inputs were wrong. You didn't have to worry about, did my workflow fail because the node I was running on-prem had problems? We'll just hope that it works tomorrow, right? Ephemeral clusters give you tons of benefits, from workflow stability to running as many clusters as you want concurrently, but most importantly, they allow you to update your tech stack per workflow instead of per cluster, because when you're testing them per cluster on a massive multi-tenant cluster, you just don't upgrade enough, and you get stuck on older technologies. So let's look at what we migrated. 3,000 Spark jobs, 300 workflows, 150 customer-facing data sets, and all sorts of inputs that were replicated. This isn't including intermediate data sets or customer-facing data sets. The most important migration is one that the customers never notice. You see, our AWS reps at the end of our migration would come to me and say, "John, what are your business partners saying? Do they love that you moved to the cloud?" I'd kind of chuckle and be like, they're not saying anything because we didn't break their stuff, which is a huge indication that we migrated successfully. Our goal wasn't to provide data faster, which we were able to achieve to some degrees. It was, could we get out of our data center? Over the course of our migration, we only had one business partner report a defect in a data set we produced. And it was really early on. It was like workflow 20, and I was really confident. And I told the developer, "Yep, ship it. We're going." But what we learned from that was one data set, one field was missing in that data set, and it caused customers to be impacted. And we learned that we needed to slow down, and we needed to do additional validation when we were going to go to production. Although that added a lot of extra overhead to our migration, the rest of our workflows never impacted customers. And as it stands today, we have decommissioned our entire on-prem Hadoop system, and we're running entirely on AWS. So let's compare and contrast. We went from 3 massive multi-tenant Hadoop clusters to 300 daily ephemeral clusters. We went from Cloudera to EMR. We went from Spark 1 to Spark 3. But most important, we were able to cut the total number of compute almost in half for a whole bunch of different reasons, but most importantly, we no longer needed to run each Spark job twice. As part of our migration, we didn't just stop creating new business features. And we didn't have those new business features, put them on-prem, and we would migrate them after. What we did is every single new business feature took advantage of the path that we set forward, but they took it farther. For the first time, Spark wasn't our only hammer, and we weren't stuck on Spark 1, so we weren't having all of these silly errors that we were struggling with. So our time to market improved because we didn't need to wait for hardware. Our DevOps process was flawless, and new technologies kind of just made it easier. But we could also use new capabilities. Apache Hoodie, these new workflows could take advantage of that incremental view of the data. They could start to combine other things like SageMaker to make even more new features. In addition, I mentioned that most engineers didn't understand HDFS. They do understand S3. And I mentioned that we catalog all of our data. But what happened is something that we weren't really expecting. Our catalog data, that UI where we exposed all the data to the entire company, spread like wildfire. And we've already had a dozen different teams come up to me and say, I had no idea this data was available. Can I get access to it? And by making your data available on S3, you just inherently now are getting new business features because different groups can see and interact with that data if they request access to it. And I want to end today's presentation by saying you guys can do it too. And I want to share with you a little bit of our process to be successful. And it starts with a proof of concept. Take a few of your strongest engineers and have them go try out all different technologies. Maybe it's not even EMR. Go try out a bunch of different ones. And then make sure you understand your key use cases. For us, there was 4 of them. Making sure we could replicate our data to AWS. Making sure we could compute our intermediate data sets. Making sure that we could create our business features, and making sure we could load our business features back to our application data stores. Develop a process that every person can follow, and make sure you set up a strong foundation so not everybody's reinventing the wheel. And then you're going to go wide, and it's going to be about creating a team. And you're going to need to have those experts. They're probably the people that started on the proof of concept, but do not take advantage of your experts. Have them train their trainers. Allow your experts to go work on more foundational items because your migration's just begun. They're going to need to tackle some more challenges that come up along your way. And you should expect the ramp-up time. For us, our team had no AWS experience. We ramped up 50 developers over 4 months. And then make sure you're leveraging AWS. Take advantage of those weekly meetings with your solutions architects. Ask them the questions that you have. Make sure you're validating your ideas and your plan with them. Ask them questions that you're stuck on. If they do not have the answers, they'll go find people that do. They'll set up ad hoc working sessions for you. And make sure you're taking advantage of the ticketing system as well. Originally, every developer that got stuck would come to me, and I would take it to the solutions architect who would ask, do you have a ticket? And then I would go back and we would create the ticket. What I found worked really well is empower your developers to make their own tickets. They can get on a call the same day with a support person, and most likely they can solve the problem. But if they can't, the ticket's already created. I can send an email to our solutions architect, and we can have a proactive conversation on our meetings instead of trying to describe the problem, get the ticket created, and slowing down the process. And then I want to end it by saying that we do have a blog and a case study being published in the next couple weeks, so check out those when they're coming out. And then I just want to say thank you, everybody, and I'm going to hand it over to Al to close the session.
Thank you, Sam, and thank you, John, for coming up on stage and sharing your stories. We saw how both Thomson Reuters and Lending Club were able to migrate their on-premise infrastructure over to Amazon EMR while saving costs and simplifying their operations. We hope you are able to learn something useful that you can take back to your day-to-day workloads, either on-premise or on Amazon EMR. We are at the top of the hour, so we will close for now. But we're going to hang back on the side. So if you have any questions, if you want to talk to us, you can come chat with us. Please let us know your feedback on how you like the session, and if you'd like to add something or take something away from the session. Thanks for attending today's session, and have a great reInvent.